Okay, so let's continue. And to motivate the rest of the lecture, I'm going to ask a few questions. The most important question is, can we trust these models? Can we trust L1, L21, all kinds of models to return the intended sparse solutions? Right. So when can we get a unique solution? When can we get a solution that's close to what we want to get? That's a big question. There's a quality question, a recovery questions. And will the solutions be robust to noise in B? If you make an error, make a small amount of errors in B, so I recover a solution that's close to what I would get without the noise. Okay. So also, how about these constraint and unconstrained models? Are they equivalent? So solving one going to give you a solution of the other. Well, if they are equivalent, then you just pick the best, the easiest model to solve. For example, the unconstrained model, rather than models with constraints. Okay. Now, how to choose these parameters in those three models? So recall, tau is the constraint on L1. So tau specifies sparsity. Mu is a weight parameter that balances L1 and the fitting. All right. And sigma is a noise level. They have different meanings. Now, if you consider one application that already have, say, the noise level, you already have an estimate of the noise level, just use the model with the noise level. Ignore the other two models. Okay. Now, or if you have a rough estimate of sparsity, you may actually find out, easy to find tau rather than the other two variables. Okay, so it's really application determined. So there's no global answer which one is the best to solve. All right. Now, but in general, if you deal with real data, and you probably have no idea of any of these parameters. There are some general ways to come up with these parameters, and I'll only talk about these here. And then after this, I won't talk about how to select parameters. Okay. There are a bunch of ways to do it. It's not just two, but a list of other ways. Now, the first way is called generality. What does that mean? So you're going to do something on one set of data, and then look at the result. Generalize the result to the other set of data. That's called generality. Sometimes people say don't generalize. It means I see they hang out together. I say he's a good guy, and I generalize he's also a good guy. That's called generality, all right? Okay, so stop generality means that. So in terms of mathematics, it means the following. So you're going to use a test data set. In the test data set, you're supposed to know the solution, all right? So you test the data set, use a test data set, and you know the solution, know the right solution, and just find out the right parameter that give you the right solution. And then, when you deal with other data, you use the same parameter, or when the data has different scales, you just scale it. Scale these parameters, all right? So what do I mean by scale? So I can roughly say that. So let's look at the middle model. The first term is linear. I wouldn't say first term linear. The first term is homogeneous of degree 1. In other words, you multiply. If your x is twice large, and you're going to multiply 2 here. Right? If x becomes twice large, you're going to multiply 2 here. But if everything here is twice large, you're going to multiply 4 here. Right? There's a square. So if on one set of data you find the best mu, if you go to the other set of data, you have to consider the scale difference. So you're going to change mu so that after the change, this term and that term will have the same level, roughly speaking. Okay? So that's what I mean by scale. Or you can do something called cross-validation. Cross-validation is very interesting. Suppose you're going to work on a set of data, and you pick a small subset of data and don't use it. Right? So you have a set of data, you use a large part of it and reserve a small set of data. Don't use it, and then you're going to work on this larger set of data, and do this. And do these solve this model, and it'll use a specific mu, and then you're going to get a recovery. And then use that recovery to test whether that recovery matches the remaining data. Okay, let me be more clear. So I say I have data A1 and A2, and I want to recover say X, and the measurements are B1 and B2. All right. So I'm going to use A1 and B1, and I'm going to reserve A2 B2. Right. So then I solve a model. I get to recover X star, but this X star depends on my parameter. Let's say it depends on parameter mu. Okay, and then I look at this. I look at A1 minus B1. Okay, and this is supposed to be the error, right? To be the noise W1, and then I do A2 X mu star minus B2, and it's going to be W2. Okay. Now, if they have the same noise, W1 and W2 should be of the similar order. Okay, the W1 and W2 should have similar statistical properties. But if W1 is much smaller than W2, then it means that I overfit it. It means that I probably choose a mu that's too big or too small. If I have a W1 much bigger than W2, it means that I treat this data very different from the other set of data. So the two sets of data no longer match, but they should match. So this is the rough idea. And of course, you can change the set A1. You can select A1 on other rows, and then use the remaining rows to add the test data. This is called a cross validation. There are a bunch of other ways. I'm not going to see them. And basically, this area is called a model fitting. Right. Just remember one word called model fitting. Okay. All right. So let's continue. So we've seen this. This is it's just notation, nothing special. Here we consider something called L21 norm. L21 means that you're gonna. So you have an X matrix. All right. So the ith row of X is written as xi1 all the way through xin. All right. So you pick the ith row, and then you take the two norm of the ith row. All right. Their total energy. You look at the energy of ith row, and then take the sum of these energies. The summation over I. Right, this is what you do. This is what you minimize. It's hard to draw a picture, but what you want to. Okay, so let me give you one example. Suppose. Actually, I can't draw I can draw an example for group sparsity, but not for this one because this high dimensional. I can't draw a picture. But what will be sparse? What will be sparse when you do this minimization? What will be sparse is the energy. The energy will be sparse. In other words, there's only going to be a small number of i's, so that the corresponding energy are non-zero. Okay. Let me give you one other example if you can understand. So I'm going to come up with an x. X has x1, x2, x3. All right, 3 components. And I do this norm. I do a special norm of x that is defined as x1 absolute value plus x2, x3 to norm. All right. So then I ask you to draw this level set. I ask you to picture this level set. Can somebody draw this level set? Somebody want to come up and draw the level set? So it's a 3D object, right? It's an object in a 3-dimensional Euclidean space. So it should be able to draw it. So what does this set look like? So any idea? Can you see it? It's a very bad drawing, but I think you know what I mean, right? So what is this? What is this axis? X1, right? And this is there's X2, X3, right? So you look for sharp things. So these two tips are sharp, right? And this skirt, the skirt is sharp, right? So you tend to, again, if you have a linear, you have AX equals B, that's a plane. When the plane touches this whatever shape, it usually touches here or touches on this circle. It's very difficult to touch just on the surface, very difficult. So you're gonna usually touch on the circle or that tip. So in other words, it's either this x1 non-zero or these two are non-zero. But when these two are non-zero, I don't really have an idea which one is zero, which one is not. Well, these two are going to be usually both non-zero. Okay. So it's a similar idea here. So this can be seen as the L1 norm of this energy. So you just take the sum. So you're going to be a small number of such energies non-zero. Okay. So in other words, L21 norm ball has sharp boundaries across different rows, which tend to be touched by this hyperplane, this affine plane. So the solution tends to be row sparse. All right. You can generalize this idea to different P and Q, and you can still get a convex norm. For example, you change 2 to say infinity. If you change 2 to infinity, this circle won't be a circle. It's going to be a square. Okay. So if you change this P, you're going to change the shape of this circle. So that'll affect the magnitudes of the rows on the same magnitudes of the entries on the same row. Right. Okay. Now you can think it as you can also treat it. This is special. Complex value signals is a special case of this. So if you write x in complex from n, so it's actually a matrix. This is the real part. This is the imaginary part. So this is xr, this is xi. Right? When people write the L1 norm of a complex number, usually it means you take the 2 norm of every row and take the sum. Okay, this is joint group sparsity. Now this is group sparsity. Group different components of X together. Group different components of X together and assign a weight if you want. Right. Again, there are people doing this research on how to come up with these groups. So here I'm using non-overlapping groups, but it can be also overlapping. You're going to lead to very interesting structures of the signal. For example, tree structures. Okay, now in addition to using different norms to enforce different structure. You can also add very useful constraints. If you know these in your application, please do add these constraints. Here are some examples. So you know your signals are non-negative, which is often true. Should add it. If you know your signal lies, every component of your signal lies in a box, in a boundary, in an interval, you should use this box or bound constraints. And these are general nonlinear inequality constraints. Now, these are usually, in practice, pretty easy to figure out, and they're going to be very powerful in some cases. For example, just the enforcing non-activity sometimes is as powerful as imposing L1. Okay? So, adding these extra constraints to your model will sometimes significantly improve the recovery quality, and in lots of cases, they will also make your algorithm converge faster because you are posting right information about the solution. Okay. And geometrically, these inequality will generate corners. This is what it means. It'll create more corners, and tend to be more sparse in some sense. Okay. Now we now try to solve these models. We're no longer talking about models themselves. We're talking about how to reduce the model into a form that you can grab an existing solver and solve it in a few minutes. Okay. So let's first think about why we want to do this. Right. So if you do an L1 minimization like this, right. So 7 years ago, do you have a solver that readily solves this problem? The answer is no. Right? Even though it's very simple, there's no solver directly solve this. Right? And the reason is because this L1 is non-smooth. Right? It's simple but non-smooth. And I wouldn't say no, but none of the efficient solvers can solve this model. Right? You can of course use something called a subgradient projection method. Calculate the subgradient of L1 and project it to the hyperplane. I can call it a solver, but it's not very efficient. Okay. Now, sparse optimization often has non-smooth objectives, and you're going to see conic programming solvers do not handle non-smooth functions. They handle cones, but not non-smooth functions. So the basic idea is to model non-smoothness by inequality constraints. All right, we're going to turn non-smoothness into inequality constraints. Here's an example. This example can help you deal with one of the exercises of the homework question. This is the L1 norm. There are actually different ways of turning an L1 norm to a very simple minimization problem. This is one of them. Right? So L1 norm is a summation of absolute values. Absolute values basically look at a number. Right? If the number is positive, I call it the absolute value. If the number is negative, I put a negative sign. Therefore, x1 and x2 are modeled like x1 will be itself non-negative, x2 will be itself non-negative, and the x1, x2 will respectively model the positive part of x and negative part of x. So, if x equals say 1 minus 5, then x1 will be 1, 0, and x2 will be 0, 5. Whatever negative goes to x2, whatever positive goes to x1. Right? So I have to devise a bunch of constraints and objectives so that this will happen. And this is how we devise it. Right? So we're going to minimize the total of x1 plus x2. So in other words, it won't come up with this situation. It won't come up with this guy's 1, this guy's 6. No, it won't come out like this. Because this doesn't give you the minimum. When you minimize the sum of x1 plus x2, it will automatically turn at least one of them to 0. So this guy will be 0, this guy will be 5. Alright? And this models, the second constraint, the first constraint that models x1 is positive part, x2 is negative part. Okay, this is one of the ways. There are other ways, and there are actually other better ways. I'm going to skip those. Alright, so now you can turn just the L1 into a small minimization problems by splitting the positive and negative part of the variable and introducing non-activity constraints. Right? Introduce inequality constraints. So these are the constraints really that cause us trouble. That models L1. Okay, now you know how to deal with this, right? So this will be a linear program because you just replace every x by x1 plus x2, and you can similarly replace this x by x1 minus x2. So this becomes a linear program. Now this is going to become a bound constraint quadratic program. What does that mean? This term is quadratic. Right? You do this kind of splitting, it will remain quadratic. This term becomes a bunch of stuff like this. But you're gonna still have these. You're gonna still have these inequality constraints, right? And these are bound constraints. So therefore this one will be reduced to a bound constraint quadratic program. Well, MATLAB can solve this problem. All right. Okay. Now, what about this model? Now, this model will reduce to another bound constraint quadratic program. Very simple, very similar to the second model. Now, this last model is a little different. The last model does not reduce to a bound constraint quadratic program. So this involves the definition of quadratic program. Standard quadratic program does not have quadratic constraints. It only has linear constraints, equality or inequality. Quadratic program, again, quadratic program does not have inequality constraints, do not have quadratic constraints. Now, this constraint is quadratic. You can add a square here, you can add a square here, right? It doesn't really matter if you have square or not. But once you have quadratic constraints, it's no longer a quadratic program. It can be reduced to something called a second-order cone program, which I'm going to tell you next. All right. Okay. But the point is, once you do this kind of splitting, everything all of these problems become standard optimization problem. So this is conic programming. The conic programming has a basic form. It always minimizes a linear objective and subject to linear equations and inequality constraints that involve a cone. Okay. So what does it mean? What do I mean by f times x plus g in a cone greater than or equal to 0 with respect to a cone? It means the following. It means this vector lies in this cone K. But there are some conditions on this cone. The cone has to be convex. Its convex set has to be closed, so include the boundary, and it has to be pointed. In other words, 0. This origin is part of the cone. There must be a point, and must be a tip here of the cone. All right, there are some standard examples of such a cone. First orthant, this is the simplest cone. It just asks all the components of x be non-zero. All right. So this is a cone. You don't think this is a cone because most of the time you think a cone looks like this. You think this is a cone. All right. You think this is the cone. This is a cone, but this first orthant is also a cone. It's called a polyhedral cone. The surface of these cones are flat. Right? The boundaries of the cone are flat. This is this norm cone or second order cone. This looks like this. Right? So t is the height, and x is the surface, is the horizontal points. The higher you go, the larger the circle you can be. Right? So this is called second order cone or ice cream cone. It looks like ice cream. This is a polyhedral cone. Polyhedral cone is just a standard linear inequality, except the right hand side has to be 0. The polyhedral cone. And here's a non-trivial cone called positive semi-definite matrix cone. Every point in this cone is a matrix. It's symmetric and positive semi-definite. All right. This cone is somewhat special. It looks like a smooth surface. All right. So if I just do a 2 by 2 matrix, and the symmetric, therefore the off-diagonal entries are the same, and then I plot these cones in 3D, I get this shape. This is a weird looking cone, but it's this cone, and this cone is very powerful for modeling lots of problems. Okay. Now let's look at the special example of this conic program. Now I'm gonna let this cone be the first example, be the first orthant cone. Therefore, I can enforce f of x plus g just greater than or equal to 0, component-wise. Right? So this is linear program. This is standard form of linear program. Every linear program can be translated into this form. It's called standard form. Right? The cone is the first order cone. The standard algorithms are the simplex method available in MATLAB. All kinds of interior point methods. Now, there's not just one, but actually a series of interior point methods. The primal method, the dual method, the barrier method, the primal dual method. And when you deal with very large linear programs, you can do something called decomposition. Use something called decomposition approach. Basically, it's a divide and conquer approach. All right. So what are the basic ideas of the simplex method? The simplex method, by the way, this is a terrible name. Simplex is a special object in geometry. Right? The simplex method is a terrible name. But the basic ideas of this method is, well, this is the affine plane. This is a polyhedral cone. This is a non-activity cone. Their intersection is actually a polyhedron. Right? Polyhedron has flat boundaries and extreme points or vertices. So what you're going to do is just move between vertices. So you're going to move from one vertex to the neighbor vertex until you reach the solution. Right? This is the simplex method. So interior point method works in a totally different way. You're going to move inside the polyhedron and keep away from the boundary, because otherwise sometimes you will have to move very small steps, or you have to traverse a lot of vertices before you can reach the solution. But when you move inside the polyhedron, you can make large steps, make very efficient steps. All right. Okay. Now, so interior point method this method, the simplex method, is very practical, but lots of interests are given to the interior point method. Now, one of the simplest way of deriving an interior point method is this way: is to consider a logarithmic barrier. It means that I'm gonna remove these constraints. I'm gonna ignore these constraints, but I'm gonna penalize. I'm gonna apply a large penalty when any of my x components get close to 0. Right? So, in other words, I'm going to set up a barrier around 0 so that your point can't get too close to 0. Okay? So, this is the barrier. Log has this shape. So, log function has this shape. Right? And we're going to do a negative log. We're going to minimize C transpose x, which is linear, minus a scalar t times the negative log, minus log. So you're actually going to minimize this, right? And this is 0. So when you get 0, you get very high penalty. When you get away from 0, you get low penalty, right? So this turns a linear problem to a nonlinear problem. So you might think this is difficult, but it's not, because this problem has no inequality constraints. It only has equality constraints. Right? What you can do is take the gradient of this term, project it to the plane, or you can do a Newton step of this objective and project it to the plane. It will give you pretty fast improvements. Okay. And what's amazing is this idea turns out to work for other general conic programs. In other words, if you change this cone to other cones, a second order cone or semi-definite matrix cone, a similar thing just work. Right? This is nice thing about barrier method. Okay, now let's look at the second order cone program. Second order cone looks like ice cream. So y is the height, the y and k is the height. The other components of y are just the flat surface. Okay. So this is very standard. This is just, let's say, this is 2 norm, this is just scalar, right? Now, it turns out the second order cone can model lots of problems. All right? There's a paper about how to model problems using second order cone programs. I'm gonna give you a reference later, all right, for this. Now, how do you apply? Well, let me go back. Now, these are the methods for linear programs. All right? The main method are these two. This is just approach that reduce a large linear program to a smaller linear programs. So main methods are these two. Do they generalize to second-order cone programs? Well, it turns out this is easy to generalize. This interior point method is easy to generalize. The simplex method does not really generalize because you're gonna get smooth surfaces. You're gonna get smooth boundaries. They're no longer piecewise linear. All right. So there's no longer vertices, or maybe you say there's infinite number of vertices in this example. All right. So the simplex method does not really generalize to this more general second-order cone programs, but the interior point methods still do. For example, you can impose this kind of log barrier to keep your point away from the boundary of this cone. Just use this log barrier. Right? Okay. Now let's move to a more powerful programs. Even the best scientists and engineers in our field are studying this model. It's called a semi-definite program. In this program, the unknown variable is a matrix, and this matrix is symmetric and positive semi-definite. The cone is, this is part of semi-definite cone. All right. So any semi-definite programs can be written in this form. It's a linear objective C dot x. C dot x means C dot x means the summation of Cij, Xij, Cij times Xij. It can be also written as the trace of C transpose X. It's the same thing. Right. There are also people write it like this, as inner product. The same thing. It's a linear function of the matrix. Even though you deal with a matrix, it's a linear in the matrix. So objective is pretty simple. This A is a linear operator. It's just linear combinations of the entries of the X, and you get B. All right. So everything here is linear. The only main interesting thing is the cone. Is the part of semi-definite cone. Now I'm going to give you the last part of the lecture. I'm going to give you an example of modeling a non-trivial program into a problem like this. All right. But for the moment, let's try to generalize this interior point method idea to this semi-definite program. Here's the idea. We're going to create a log barrier. But how do I create a barrier for this cone? It's very simple. It's log of the determinant of y. All right. This is a concave function. If you look at the textbook convex program by Boyd and Vandenberg, you're going to find a proof. It's pretty simple to prove this, actually. This is a concave program. This is a concave function. All right. Then this is how you. I skip all of these. I skip all of these. This is how you would do. This is what you will do in a interior point method. All right. So again, this is the original objective. This is a linear function f0 of x, and this is the barrier. Right. This is negative log. This term, when you minimize this term, it's going to keep you away from the boundary. You can't touch the boundary because if you touch the boundary, you're going to go to infinity. Right. Therefore, when you minimize it, you can't really touch the boundary. But there's a parameter t that controls the strength of this. Right. The t will balance the original objective and the objective of keeping you from the boundary. All right. Now, what you're going to do is fix a t and calculate the solution of this problem. Now, this is a nice program. It has a convex, actually strictly convex objective subject to only linear constraints. There's all kinds of ways to do this. For example, Newton's method to solve this problem. Now, suppose for fixed t, you get a solution x star t. All right. Then you change t. And when you change t, you're going to get a path. Right? When this t goes to plus infinity, this term will be ignored. Only this term will dominate. Right? But this term is sufficient enough to keep you go out of the boundary. So what you're going to do is you're going to get a sequence of solutions that converge to a point. And this curve is called central path. And this point is a solution. This provably a solution. Okay. Now, what you actually solve is you're not going to follow this path closely. because you're not going to waste all your time calculating a specific solution for a specific t and then change t. What you're going to do is you fix a t, do one or a few Newton steps and change t. So you're going to do basically zig and zag around this central path until you get close. Right? So this is the interior point method, more or less. Alright. Okay. And so I ignore all the details. I assume you know how to do Newton's method, and this will be the complexity, a number of iterations for you to reach a solution that's epsilon away from the true optimal solution. Right? Epsilon is the accuracy, t is initial weight, and there's something called theta and mu. Theta and mu will be different for different type of conic programs. That's this page is about. For linear programs, they're going to be a theta and a mu. For another program, they're going to be different theta and mu. All right. Okay. The key point is this is a polynomial time algorithm. Why is that? Because the accuracy epsilon is a small number, right? So 1 over epsilon, or epsilon on the denominator, it will give you a large number. This large number is inside log. When you have the accuracy inside log, this is the polynomial time algorithm. Okay. So that's just like a few minutes about the interior point method. So you basically know what the algorithm will do when you call the algorithm. There are other type of interior point methods. The most general yet efficient, the generally most efficient algorithms are primal dual interior point algorithms. They're going to set up the KKT conditions you learned last lecture. So they set up the KKT conditions. Everything in the KKT will be nice except the complementarity constraints. So the complementarity constraints look like the following. Xi is the primal variable, Si is the dual variable. They have to the product have to equal to 0. Xi is unknown, Si is unknown. So they're both unknown, but their product have to be 0. All the other constraints are rather simple. In terms of linear programs, all the other part of the KKT conditions are A times X equals B, X greater than or equal to 0, A transpose Y plus S equals C, S greater than or equal to 0. But all of these are linear constraints, except this guy is nonlinear. Alright? So how people do it, they're going to change it to mu. Right, this is for all I. You can change it to mu, and then ignore these non-activity constraints and solve for this problem, and then change mu. This is basically the primal dual interior point method. So you're going to update both the primal and the dual variables at each iteration. There's no distinction between inner and outer iterations. It often exists as superlinear asymptotic convergence, and basically they converge really fast. And the search directions, how do you move from one point to the another point? You're going to basically use Newton direction for the modified KKT conditions. You can even start. You don't have to start from a feasible solution. There's a way to come up with a homogeneous, come up with a larger KKT system that's called homogeneous, and then you don't need a feasible start point. And the cost per iteration is the same as the barrier method, and you have all of these benefits. All right? If you have no ideas of what I'm talking about, it's fine. All right? Okay. The bottom line is it's fine. I mean, if you know this, it's fine. If you don't know this, it's fine. But all you need to know is primal dual interior point methods are good. Okay. And so when you have choices, when you download the code, you have choices. Choose this. Or try this first. All right. Okay. Now we're gonna solve it. We're gonna translate this problem into something that can be solved by interior point method. This is what we need to do. This is more important to you. All right. We're going to do 2 examples. First example is L1. The second example is nuclear norm. After this, we're done. We're done for today. Okay, let's first do L1. So we have to be slow here. All right. So this is the first line is the original model. This is the original model. It has a L1 term you have to deal with. It also has this quadratic term you have to deal with. You have to translate it into a standard cone program. This is how you would do it. First, apply the trick that split x into two variables. Alright? It split x into the positive part and its negative part. Therefore, x is going to equal to x1 minus x2. Therefore, you're going to replace this x as x1 minus x2. Alright? So, you have dealt with the constraint, you have dealt with the splitting, now you deal with the objective function. The objective function is the L1 norm, which is the absolute value. So you just need to sum up the objective, sum up the positive part and the negative part. Right. So this is very standard. It's called variable splitting. Split x into the positive and negative parts. You made a trade-off. You no longer have a non-smooth function. You have a linear objective function, but you have inequality constraints. But these constraints are now x1 and x2 lie in a first order cone, right? So you treat non-smoothness for cone. All right. Okay. But now this part is not clear what this is, so we still have to do more work. Now there are two steps here. Actually, there are two steps here. The first step is I'm going to introduce a y, a variable y, a natural variable y, so that this entire term equals y. Alright, so ax1 minus ax2 plus y equals b. So y gonna swap this thing out of the two norm. Okay? Once you have y, once you introduce the y, you're gonna have y 2 norm less than or equal to sigma. Right? This is what you need to handle. And how do you handle this? You introduce the z. So if you let this one be z and z be sigma, now this is a second order cone, right? This is a second order cone. Then you let z be sigma. I think I probably don't need any t. I don't think I need t. I don't know why t is here, but I don't think I need t. Right? Let me see. Why is that? Okay, I think I don't need t. What I did was this. What I did was this. It's stupid. So I did this, and I did this. All right. So I didn't let z equal to sigma. I let z less than or equal to sigma. Now z less than or equal to sigma. I mean, you can't have inequality constraints if z is already part of the other cones. Right? So what I do is I let z plus t equals sigma and let t greater than or equal to 0. Alright? Okay? This is what I did. But I mean, this is larger. This is just a larger program. It still gives you the same solution there, but it just did something unnecessary. You can get rid of t. Right? Okay, now this is the problem you're gonna feed. You're gonna feed one of these solvers. You're gonna have to do this yourself and feed to these solvers. Any of these solvers will solve this problem. Alright? If you don't even want to do this, if you're lazy, you don't want to even do these, it turns out these two modeling languages will do this. Alright? It'll do these for you, do this reduction for you. Maybe in a very inefficient way. Now because they do it automatically, they probably do this instead of getting rid of t. They probably even do something worse. Alright? So one of the projects, by the way, one of the project topic will be a study of CVX. Right? I'm going to ask you to study CVX. CVX is something very nice that will reduce a large set of convex programs to a program like this that can be fed to a conic programming solver. Right? So it's called disciplined conic program or disciplined convex program. So I'm going to ask some of you to form a group to study CVX and then apply the same discipline to something called first order algorithms. Okay? I'm going to specify it later. But there's lots of interesting things about this model. about this modeling language. Alright, so this is simple exercise. The next exercise is not as simple. So let's try to do this. Let's try to minimize nuclear norm. Nuclear norm is the summation of the singular values of the matrix X. It's highly nonlinear. I can tell you it's convex. It's actually pretty easy to prove it's convex. But how do you translate it into a standard conic program? Okay. So we're going to minimize the summation of the singular values of X subject to a bunch of linear constraints, and it's supposed to give you a low rank solution. It's very interesting. Now, how people do it? How people reduce it? To reduce all of these to a semi-definite program. Okay. By the way, if you don't minimize nuclear norm, you minimize, say, trace or spectral norm, it's becoming easier. Right? For example, if you minimize the spectral norm is the maximum singular value. Just the maximum. Spectral norm, you minimize spectral norm, or you have a spectral norm constraint like this. You can very simply translate it into a bunch of inequality constraints using cones. Here is how you translate it. You're going to introduce a vector variable t for alpha, so t less than or equal to alpha, or t equals alpha. And then you require t times the identity minus x is positive semi-definite. So t minus x positive semi-definite is equivalent to t times identity. T times identity. How do I? Okay. Well. Well, this is equivalent to t greater than or equal to all the sigma i's of x. All right. I don't want to do the proof because the proof is simple. You just do a singular value decomposition. Right? Actually, you don't have to not singular value. Do a spectral decomposition because this is a symmetric matrix. I'm talking about. Oh, okay. Well, I'm not. Let me see. This is a square matrix. To do a singular value decomposition, and you can do this. All right. Now let's deal with nuclear norm. Let me motivate the approach. So at the end of the day, I'll tell you the solution. The solution is this. The nuclear norm will equivalent to this. The nuclear norm will equivalent to minimizing half of the trace of some other matrix, and then this matrix has linear constraints, is symmetric, and positive semi-definite. Right? This is the nuclear norm. Once you know how to do this, you just plug this one into the original problem. You're going to reduce it to a semi-definite program. So the trick is, how do you come up with this, or in other words, come up with this? All right. So let me motivate it. Okay. The first thing, let's try to deal with an absolute value to just get some ideas. All right. This is not trivial. So absolute value, you can write an absolute value like this. You let y and z be non-negative, and let the square root of y times z be greater than or equal to the absolute value. Alright? If you assume these constraints, if you assume these hold, then half of y plus z going to greater than or equal to, this is Cauchy-Schwarz inequality, and then use this, therefore half of y plus z will be greater than or equal to the absolute value of x. Right? Which means, if you minimize y plus z, you minimize the absolute value. But this hold provided that they are non-negative and this strange inequality holds. Alright? And it turns out, when you minimize this, it actually can equal. All of these can equal if you set y and z equal to absolute value of x. Okay? Now what are these? I can write this one equivalently as a positive semi-definite constraint. So y and z are non-negative, means the diagonal entries are non-negative, and y and z multiply square root greater than or equal to the x absolute value, means that this matrix is positive semi-definite. Now this 2 by 2 matrix is positive semi-definite if and only if, I think you should know this, is if and only if the diagonals are all non-negative and y times z greater than or equal to x squared. Then this matrix will be positive semi-definite. Okay. Therefore, if you impose this positive semi-definite constraint, you automatically have this inequality: half of y plus z greater than or equal to x absolute value. Right? And the equality can be attained. Therefore, absolute value can be written in this crazy form. It just minimizes the trace, minimize half of y plus z. That's the trace of this matrix, and then you require the off diagonal terms to equal to x. So this means that you pick out the top right entry of M. It has to equal to x. M is symmetric and M is non-negative, is positive semi-definite. Right, this is a crazy way of writing it, but using this you're going to be able to deduce a Newton norm thing. Alright, this is just some motivation. Sparse calculus for L1. Now, this is a sparse calculus for Newton norm. Now, consider X, and I assume X has fewer rows than columns, and X is not necessarily a square matrix, it's just a rectangular. So let's try to impose this thing. This is just a mimic. This is just a mimic of this guy. Right? I replace these little entries by matrices. Right? So do some mimic. I mimic that. So y and z on the diagonal, they're block diagonals, and then x is the off diagonal block. All right. So we're going to do a singular value decomposition. Singular value decomposition basically is to turn an x into a diagonal matrix. All right. So any x matrix can be written as a rotation. V is orthogonal, so V is a rotation. Maybe reflection as well, and times scaling and times another reflection or rotation. Right? Any matrix can be written in this way. This is singular value decomposition. All right. Then once you write it that way, the Newton norm are just the summation of the diagonals. All right. Then I just apply this singular value decomposition idea to turn this crazy matrix basically into a matrix look like this. This is the idea. So this is how you do it. You just left multiply and the right multiply some like the singular vectors, which are going to cancel things out. All right. So you just do this and do this multiplication. Now I skip the details. All right. At the end of the day, you get this term plus that term minus 2 times sigma greater than or equal to 0. Oh man, being positive semi-definite. What is this? Well, this sigma is a diagonal matrix which has all the singular values on its diagonal. Right? You're almost there. Okay. Therefore, you just take the trace of this guy. Take all the sum up the diagonals. Trace is linear. When you take the trace of 3 matrix together, you're just taking the trace of each one. So take the trace of y. It turns out the trace is unaffected by the unitary transform. This is unitary invariant. Right? So I need to tell you this. So trace of a matrix, let's say y, is equal to trace of y u transpose. Is that right?
Yes.
Yeah. So because this is the identity, okay, and there's a well-known property of a trace. Trace AB equals trace BA. So in other words, whatever left it can move to the right, right can move to the left, because trace is just a component-wise multiplication. Therefore, you can move the last u transpose to the left. So therefore, it equals the u transpose yu. Right. This is the reason. The trace is unitary invariant. So you see two unitary matrices, you can get rid of it. So trace of this guy, trace of this guy, or trace of this guy is just the trace of y plus trace of z minus 2 times the nuclear norm of x. This is exactly like this. Right? This is just exactly like this. It's the same thing. Right? So it's just a generalization of the previous page. Right? And you can attain the equality by setting special y. If you set y like this, set z like this, you actually get the equality, which means you can minimize this. If you want to minimize nuclear norm, you can just minimize half of the trace y plus trace z. The same thing. All right. Therefore, it's at the end of the day, it's very simple. The nuclear norm is equal to the minimization over two unknown variables, y and z. You minimize half of their trace summation, subject to this inequality have to hold. But this inequality, okay. Now the problem of this inequality is, I mean, you can't. So when you have this one, this is not a standard. This is not a standard constraint in a semi-definite program. Semi-definite program says you can only have an entire matrix that have this. All right. This is what is allowed. This is not allowed. So what you do is you let this entire matrix be M. Let this entire matrix be M. Say M is symmetric. M is positive semi-definite, and the corner of M equals X. Just pick out the corner of M equals X, and then just minimize the half of the trace of M. That's it. All right. So we're almost done. So it means we're going to assign you homework questions, ask you to download some data and solve problems like this using CDX, using CDX or one of these solvers. Up to you. All right. And you should be able to use this formulation and to solve some of the nuclear norm problems, and then try to observe whether your solution is low rank. Alright. Okay. There's some other tedious stuff of practice of the interior point method I'm going to skip, because this is not a course about the interior point method. You can read them. You can read them and use them. Okay. I'll tell you some of these papers, some of the references to solve very large-scale semi-definite programs. This is a very nice paper, and this is my code that solve matrix completion. This is another work with Zai Wenwen from Shanghai Jiao Tong University. This is the method that solve very large-scale conic programs, not using interior point method, but the first-order methods. There are also something called a matrix-free interior point method. Matrix-free, it means that it does not form some huge matrix in standard interior point method. You can take a look at those. All right, and the last page, very last page, subgradient method. I just feel I should mention this because there are people who apply subgradient method directly to this model. I mean, or apply subgradient projection method directly to this model. The good thing is simple. It only take a few minutes to derive the algorithm. It's very easy to code up. The bad thing is the convergence is very slow, and usually requires the step sizes to diminish in the limit. All right, I'll tell you the reason in next lecture. There are some further readings about this stuff, and I put the links here. By the way, you probably won't be able to use this shortened link because these are from Google. So if you want to find out these links, let me know. I'll translate them to a full link. All right. So that's it for today, and I'll tell you what we're going to do tomorrow. And I hope you can preview the lectures. Tomorrow will be. If you get bored today, you will get bored tomorrow as well. Even bored. Tomorrow will be all the mathematics about the recovery guarantees. A lot of inequalities, and lots of log and other things. All right. Okay, so much for today, and so I end early. So I will be here for maybe 20 minutes, and if you have questions, come up here. All right.